Okay, so we've got an RC circuit here, and I find it usually helps to draw it. So we have a resistor and a capacitor. Okay, so we have a switch S, a resistor, and a capacitor. And we're told that the battery has an EMF of 24 volts, and the resistance is 325 ohms. Alright. And then we're told that at t equals 0.24 seconds, the voltage drop across the resistor is 11.2 volts. Okay, so where this is 24 volts. Alright, so what's the voltage drop across the capacitor at that time? Well, that's easy. That's the loop rule, right? We know that the voltage drop across the resistor plus the voltage drop across the capacitor is equal to the EMF of the battery. Right? So 11.2 plus the voltage drop across the capacitor is 24, so the voltage drop across the capacitor at this time would be, what is that, 12.8 volts. That's not too bad. Okay, part B. What is the capacitance of the capacitor? Now this is going to involve some logarithmic math, so let's see. Let's do, I guess we'll do the voltage drop. Well, okay, the current I is equal to I max times e to the minus t over RC, right? But if I multiply both of these by, well, okay, now remember I max is the EMF divided by the resistance. Well, now if I multiply both sides of this by R, then I get that the voltage drop across the resistor is equal to the EMF times e to the minus t over RC, right? So that's, we're given that as 11.2 is equal to 24 times e to the minus t over RC. Okay, so if I divide both sides by 24, I get 0.467 is e to the minus t over RC, and now I take the natural log of both sides. That gets rid of the exponential. The natural log of 0.467 is 0.762, and it's negative. And that's equal to the time over RC. So now the time, I'm going to go ahead and plug in for time, 0.240, and I'm going to plug in 325 for the resistance. Now if I solve this equation for C, I get that C is equal to negative 0.240 divided by 325 times negative 0.762. So the two minus signs cancel out, and I'm left with 9.7 times 10 to the minus 4 farads for the capacitance. It's a realistic value. Okay, part C. At what time will the capacitor be 85% charged? Alright, well, let's start with tau, I guess. It'll just save me some time to do this. Tau is equal to resistance times the capacitance, and that's 0.315 seconds, using this value for the capacitance and using 325 for the resistance. Okay, so we'll use the equation that the charge on the capacitor is equal to Q max times 1 minus e to the minus t over tau. Right? And Q over Q max is 0.85. Right, we're at 85% capacity. You know, Q is equal to 85% of Q max. Okay, so if I make that substitution, then I get 0.85 is equal to 1 minus e to the minus t over tau. Alright, so now I've got to rearrange this, and this is 0.15 is equal to e to the minus t over tau. And then I take the natural log of both sides. And then that gives me negative 1.90 is equal to negative t over 0.315. And if I solve for t, I get 0.60 seconds. Alright, let's think about that for a second. So we want the capacitor to be 85% charged, and this T is roughly 2 tau, right? And we know that after 1 tau, we're at about 63% charged, so 2 tau being 85%, that seems like a reasonable answer.